Hello. In the previous sessions, we have applied the Maxwell's relations in thermodynamics to obtain two relevant results, namely the TDS equations. We could obtain the first TDS equation and the second TDS equation, and I had suggested you to try deriving the third TDS equation. There are a number of applications for each of these TDS equations, which you can refer to the given reference materials. And in this session, we are going to discuss another relevant relationship in thermodynamics, which can be derived by using the TDS equation that we have already seen. So we can conclude that the equation known as Clausius Clapeyron equation, which we are going to derive, is ultimately an application of the Maxwell's relationship. As we have seen, Maxwell's relationship helps us to connect or find out new quantities or hard to measure quantities in terms of the easily measurable or easily controllable quantities. So let's try to understand what is the use of Clausius Clapeyron equation, in which topic it becomes relevant, and what is the physical meaning that is given by this particular relationship. So in order to understand the use of Clausius Clapeyron equation, I draw your attention to PT diagrams, the pressure temperature diagram of thermodynamic systems. So at the bottom of the screen, I have included two PT diagrams, the pressure temperature diagrams, which may look almost identical, but there is some difference, some notable difference. If you are observing the two diagrams with some care, you can see there is a lot of similarities, of course, but there is a major difference. So try to find out the difference. By the time we'll have some acquaintance with what actually is a Clausius Clapeyron equation, this thermodynamic relationship is especially useful when we deal with phase transitions. So they are used in analyzing the phenomenon of phase transitions. You are familiar with the concept of phase transitions, the simplest thing being conversion of ice to water on heating, and again liquid water into vapor on further heating. So in the case of water, which may exist in three different states, the solid, liquid and the gas, we can consider the change that happens with the change in the temperature of water as some sort of a phase transition. We are able to identify the solid, liquid and gaseous phases of water. And as we have seen already in our earlier discussions, that the phase transitions in general are classified into two categories. One is known as the first order phase transitions. First order phase transitions. And the other one is the second order phase transition. So that is a broad classification of phase transition, and this phase transition classification was done by the physicist named Ehrenfest. So it is also known as the Ehrenfest classification of phase transitions. Ehrenfest, who was actually a person who followed the theories of Boltzmann and like Boltzmann and first also ended his life by himself. There is some sad stories in the history of thermodynamics. Anyway, come back. So the transitions, phase transitions are in general classified into first order and second order. And what is this order and all, you will learn. Okay, you can just refer to this one. I don't spend time on this one. This order relates to the derivatives. Okay, so first order means first derivative and second order means second derivative. It depends on whether the first order derivative of certain quantities are continuous or not. It's a mathematical definition. Anyway, I can simply tell you something, that the first order phase transition are generally phase transitions which involves some latent heat. So that is a very simple method to identify a first order phase transition from the rest of the kind. So involves latent heat. So there is a characteristic, so that you can very easily remember, like, so wherever there is a latent heat involved in any phase transition, you can just classify it as first order phase transition. So the best example, like the transformation of liquid water into steam, or from ice to water, or from some solid substance. So if it is directly getting converted into say, okay, vapor, wherever there is some latent heat involved, okay, either latent heat of vaporization or latent heat of fusion or latent heat of sublimation, whatever it is, such phase transitions are generally classified as, they belong to the category of first order phase transition. Even though that is not the actual criteria, but this is a characteristic property of first order phase transition, which is easily, okay, for a beginner, okay, in the undergraduate sessions, you can easily remember this particular property to identify it and remember it. Okay, and so the examples are common phase transitions of liquid water. Now, as an example of second order phase transition where there is no any latent heat involved, okay, see, the best example I can tell you is like you have learned that if you have a ferromagnetic substance, okay, so example, I will give you example. If you have got a ferromagnetic substance, okay, in magnetism you have learned about ferromagnetic substance, which are characterized by the presence of something what is known as magnetic domains, okay, some short range order, some volumes, some very microscopic volumes inside iron and all, ferromagnetic, which are naturally ferromagnetic. So if you heat a substance, a ferromagnetic substance, above a critical temperature, which we call as the Curie temperature. So I'm just heating the ferromagnetic sample above its characteristic temperature known as the Curie temperature. You have learned that this substance will change its magnetic character to what is known as paramagnetic substance. So a paramagnetic material, I'm just in short I'm writing PMM, paramagnetic material. So you can see that the overall behavior of a ferromagnetic substance will be getting converted into another behavior. So these two behaviors are distinctly different. So we say that the magnetic material can exist in two different phases here. Either it can exist as a ferromagnetic substance below a certain temperature, and if the temperature is raised above a critical value known as the Curie temperature, its properties will show a drastic change. So we'll say that there is some sort of a phase transition occurring. That is a way in which we discuss. So there is a phase transition from ferromagnetic to paramagnetic phase, right? So this type of a transition do not involve a latent heat, and we usually classify them as what is known as the second order phase transition. There are several examples, okay, like conductor to superconductor and vice versa, like whatever it is. So in order to analyze the phase transitions which involves a latent heat, the Clausius Clapeyron equation is quite useful. So that is where usually the Clausius Clapeyron equation assumes relevance in thermodynamics. Usually this equation, which I think I can just call it as some CC equation or something like in short to say, okay, telling that. So the CC equation or the Clausius Clapeyron equation is also known as the latent heat equation, because it can be expressed in terms of the latent heat. Even though it has got several forms, it's the Clausius Clapeyron equation, when it is expressed in terms of the latent heat of the system, then that will be known as the latent heat equation, or the first latent heat equation. There are several latent heat equations also. Okay, there are some a number of name equations, phenomena in thermodynamics, like you learned in organic chemistry. Whenever you learn organic chemistry is famous for a large number of name reactions, right? Okay, similarly there is a large number of name phenomena equations in thermodynamics, and Clausius Clapeyron equation is one of that. Okay, so in general I can say that a Clausius Clapeyron equation is a general relationship between experimentally measurable quantities, experimentally accessible quantities, derived from first principles. Derived from first principles means what? Derived from theoretical concepts of first and second law of thermodynamics. That is my first principle. First principle means which has got a sound theoretical basis. That is meaning of first principles. Okay, you don't get it empirically, you don't get it experimentally, but you have got a solid foundation, theoretical foundation. Such things are what is known as what? First principles. Especially useful in studying phase transition. So this is the arena where you are going to apply the Clausius Clapeyron equation. And you can just see the figure A and figure B in the diagram. Okay, these two are PT diagrams. So we have been using PV diagrams or as indicator diagram in all our previous topics, whereas you know that the PT diagram is also able to give you some meaning. And usually in studying phase transitions, we will be depending on mainly the PT diagram. So the PT diagrams are usually known for the phase transition. So they are also known as the phase diagrams. The PT diagrams are also known as the phase diagrams. The reason you can clearly understand, because we have seen that the first order phase transitions, usually the first order phase transition which involves latent heat, that happens at some fixed temperature and fixed pressure. Okay, first order phase transition like fusion, boiling, sublimation, all are taking place at constant temperature and pressure. For example, water boils. Okay, at the atmospheric pressure, water boils at 100 degrees Celsius or 373 Kelvin. So you can see that the boiling phenomena happens at one particular pair of pressure and temperature. Okay, so as long as the phenomena of boiling happens or it is not completed, the pressure and temperature of the system is not going to change. If the pressure you keep constant throughout the process of boiling, the boiling temperature also will be remaining what? Constant. Okay, so that is one reason why we are depending on the pressure temperature diagrams in order to study the phase transitions. That is one reason. You can use other equivalent variables also, but this is a very common method that we are following. Now you look at the PT diagram which I have shown as figure A. This is the PT diagram that is for simple systems. Okay, simple systems which do not show any sort of anomalous behavior. Why I say about anomalous behavior, see, we have learned about the anomalous expansion of water. You have discussed about anomalous expansion of water, and we have seen that the density variation of water is something quite different, right? Okay, so the figure A actually shows the PT diagram for simple systems which do not show any anomaly in its expansion. And the right side figure, which is the figure B, is actually representing specially the PT diagram, the phase diagram for water. So this is for water, this diagram is for water, and this diagram is for some simple systems, okay, except water, because water is having some anomalous behavior, right? Now what is the major difference? You can see that we start from here. So there are three major curves here. You have already learned about this particular diagram and all in your class 11th or class 12th. I think in chemistry classes you have learned about this one, I'm sure. And there are three curves here. You can see the first curve here, what I'm just is from the origin which goes up to a point over here. We can see that this particular curve, this is the curve that I'm just talking about. This curve is known as sublimation curve. You can see the PT diagram is divided into three regions by the three curves. One known as the sublimation curve, other known as the vaporization curve. This one is the vaporization curve, and other known as the fusion curve. And it is converting, or it is just dividing the PT diagram into three regions. One region to the extreme left is a solid region. So this represents a solid region. Okay, so you can always understand this one. And one here is known as the vapor region. Okay, so the region here. Okay, so you can just see that if you want, you can just shade and show it. Okay, so this region is the vapor region, and the in between region is the liquid region. Okay, so this is the liquid region here. And you can see that the curve which separates the solid and the vapor is what is known as the sublimation curve. You can just see that diagram here. That is a sublimation curve. And see the one. Okay, so just let me rub it off. And the one which separates the solid and the liquid is what is known as fusion curve. Solid and the liquid is what is known as fusion curve. So this is a fusion curve. Okay, and the one which separates, of course, the liquid and the vapor. Okay, liquid and the gas, or I can say liquid and the vapor, is what is known as the vaporization curve. So it's just okay, used from the solid to liquid. That is a common transformation on changing the temperature, solid to liquid. Then liquid to vapor, that is also a common thing. And in certain cases, some substances will be directly getting transformed into vapor from the solid state. For example, camphor and all. Okay, so that process is known as sublimation. This process is known as sublimation, and this process, solid to liquid, okay, is known as melting. Okay, and the reverse is known as liquid to solid is known as fusion, melting and fusion. Okay, liquid to vapor is known as vaporization, and the reverse process is known as condensation. Okay, so that is the reason why these curves have got its name. That's the basis. Okay, so just look at that. It is separating which all regions. Okay, so solid and vapor. You can see that solid and vapor. This particular graph, which separates solid and vapor. So solid and vapor. You can see that. So these three are there. So of course that should be connected by the sublimation curve. You can see. Similarly, solid and liquid. You can look at here. This is a solid region and this is a liquid region. So they are connected by a curve. What is known as, this is a curve here. So this curve, solid to liquid, is known as the either melting, or from liquid to solid, you can call it as fusion. So it's usually known as the fusion curve. Okay, and the other one, of course, will be what? The vaporization curve. So you can see that, right? So they are named like. Now just you come to the PT diagram in the case of water, how it is different. PT diagram for water, how is it different? Okay, so you can see that the sublimation curve as well as the vaporization curve are identical with the figure A, but there is a difference for the fusion curve. You can see, unfortunately I am not able to write over this one due to some technical difficulty, but you can understand, I think. See that the sublimation curve and the vaporization curve both are identical with the that of simple system, which do not show any anomalous behavior. But water, due to its anomalous behavior at low temperatures, which we have already learned, you can see the fusion curve is showing some difference. Okay, you see the positioning of the slanting of the fusion curve. So what you can understand is that so the major difference is this one. See, you can see in the case of figure A for simple systems, the slope of all the three curves are positive. Slope of fusion curve, vaporization curve, and the sublimation curve, all the three are positive. Why do I say the slope is positive? The slope is positive because it is showing, okay, now with what is the slope of this particular graph? Slope is dy by dx, right? So slope is dy by dx. That is, okay, dy by dx means dp by dt. I can say like this, no? dp by dt is pressure, temperature. So dy by dx for all the three curves will be positive in the case of what? The simple systems shown by figure A. Because that is why, okay, you can see that even though the slopes are different, all the three curves are showing a right side slanting. All the curves are slanted towards the right. It means that as you increase the temperature, the pressure also is what? Increasing, right? Okay, but you look at okay, the figure B, which is the curve for water. You can see that both sublimation curve and the vaporization curve are slanting towards the right, means those two curves are having positive slope, but the fusion curve is what? Slanted towards the left. What does it what does it mean? It means that, okay, you can see that with the increase in temperature, okay, or with the increase in pressure, there is not okay, corresponding increase in the temperature, or the PT relationship is not okay, directly what do you say that it's not showing an increase. So if there is a dP, the corresponding dt will be what? It can be negative. Okay, so that is due to the anomalous behavior of water. Okay, so that is a notable difference. I just wanted to tell you about the difference between water phase diagram and simple system phase diagram. Okay, that is something will be helpful to always remember that even though the phase diagrams are looking similar, there is some difference in the case of water due to its anomalous behavior. Okay, now why I mentioned about all this dp dt and all, because you will see that the Clausius Clapeyron equation, which is our topic today, will be actually giving you an expression for dp over dt. So the Clausius Clapeyron equation that we are going to derive shortly in the next session will be giving you an expression for the slope of the PT diagram for a given system which undergoes a first order phase transition. Okay, and these three curves that we have discussed here, namely what is known as what? The sublimation curve, the vaporization curve, and the fusion curve. These three curves are known as coexistence curves. These three curves are known as what? Coexistence curves. You know what is why it is known as? Because coexisting. What is meaning coexisting? The meaning is that along this curve, along the okay, coordinates of this curve, or along this curve, you can see that the solid phase of the substance and the liquid phase, the vapor phase of the substance will be existing together. Okay, or you can see that along the along the fusion curve, along every point on the fusion curve, you will see that the solid phase as well as the liquid phase of the system will be coexisting. Means you will have certain amount of solid and certain amount of what? Liquid. Okay, and what is the meaning that along the curve it coexists? Along the curve means, you know, when you move along the curve, what actually is changing? You can see that see, for example, let me take a point somewhere here. So I'm taking a point somewhere here on the sublimation curve. So corresponding to this point, there is a temperature value, say T1, and corresponding to the same point, there is a pressure value, say P1. It means that for at a pressure P1 and at a temperature T1, if you are able to maintain a pressure P1 and a particular pressure temperature for a given system, then there will be certain amount of solid, and if you give some heat, you give some heat energy, you go on giving heat, so there will be certain amount of solid remaining, and there will be certain amount of what? Vapor. Okay, or solid will be constantly getting converted into vapor at this pressure and temperature. Okay, so in the system there will be solid as well as what? Vapor. Right? Now if you change, or if you are changing the temperature, or if you are performing the experiment at some other temperature, say T2, or you say that if you are changing the pressure, you are changing the external pressure, say that P2, then what will happen? Is that again the solid and vapor can coexist, but it will be coexisting at yet another increased temperature T2. When the pressure is changed, there will be a change in the temperature. So see, at P2 and T2, at this temperature and pressure pair also, P2, T2 also, there will be a coexistence of the same substance. Means all along the curve, all points along the curve are characterized by a pair of pressure and temperature. So corresponding to each pressure value, there will be a corresponding value for the temperature. So at all these pressure and temperature pairs, okay, what will happen? The solid phase and the vapor phase of that particular substance will be coexisting. Similar is the case of what? Similar is the case of what is known as fusion curve or vaporization curve. Okay, say corresponding to every point, you will be able to get a pressure and a temperature. So all these pressure temperature values will be a characteristic of the particular system where those two phases will be coexisting. And you will see that there is a special point here in the PT diagram where all the three coexistence curves are coinciding. The three curves are meeting at a particular point. So logically you can conclude that if the pressure and the temperature, let me call that one as some P0 and T0, some special values of pressure and temperature for a given system. Remember, these values are different for different systems. For water it is one, okay, for some other liquid it is something else. Okay, so it is characteristic of the system. It depends on the nature of the system. Okay, so at a particular value which I am denoting by T0 here, so say that this is T0 and there is what corresponding pressure what is known as P0, you will see that all the three curves are meeting, which means that at that point you can see that at that point what will happen, the solid phase, the liquid phase and the vapor phase, solid, liquid and the vapor phase, all the three will be coexisting, and hence we name that point as triple point of the system. Triple point. We have discussed about triple point of water and all. Okay, so at a particular temperature and pressure, so triple point. So what is meant a triple point of a system in phase? Okay, so it is the value of pressure and temperature, or it is that point in the PT diagram. Means it is a particular values of the coordinates of pressure and temperature at which all the three phases, namely the solid, liquid and the vapor phase of the system is coexisting in equilibrium. Coexisting means they are in equilibrium. Okay, it means that at that particular temperature and pressure, there will be certain, if you have a given amount of substance, then a part of the substance will be in solid form, a part of the substance will be in liquid form, a part of the substance also will be in what? Vapor form in the container. That's the meaning. So all the three will be in a particular coexisting thing. Okay, that is something what is very important, right? Now, so just look at the difference between the two curves and all, try to understand. And our Clausius Clapeyron equation is going to give you the slope, some information on the slope of the system. Means you are trying to take the dy by dx. So here it is dp and here it is dt for this curve. So it will give you some information about the the physical quantities across liquid and vapor. So if you find out dp by dt for this curve, you will get information on the solid and the liquid phase of the system. And if you take a dp by dt for this particular sublimation curve, you will get information regarding what the solid and the vapor region of the particular system. Okay, so now you will be able to read and understand the second note. So it Clausius Clapeyron equation relates the slope of the coexistence curve in the PT diagram of a substance with changes in specific entropies and specific volume of the two phases. Okay, so just note the word here, specific entropy and specific volume. So in one of the beginning sessions of thermal physics course, I told you that specific quantities means that quantities, physical quantities, when divided by their mass, they are usually known as specific quantities. For example, you have got entropy S. Capital S denotes entropy of a system, means having some m mass. So from S, if you divide the total entropy of a system having a mass m by its mass, you will get specific entropy. So it is denoted by small s. Small s denotes specific entropy, and specific entropy is nothing but entropy per unit mass of the substance. So it will be joule per Kelvin per kilogram. That will be the SI unit of small s. Okay. Similarly, you have got volume. capital V. Capital V may be the volume of say a certain amount of substance. Okay, say 5 kilogram of substance, the volume is capital V. Now you divide the volume of the total volume of the substance or sample by its mass m. Then you get what is known as represented as small v, and the small v is known as the specific volume. So why do we do this? That's also told because these quantities like entropy, volume, etc. are intrinsically, or they are inherently what is known as what I can call they are known as extensive variables, right? Hope you remember the classification of variables into extensive and intensive. Okay, so they are extensive variables, whereas the specific values of the quantities are intensive variables. So this s and small v are intensive in nature. So actually what we are doing is that we are converting the extensive variables into intensive variable by just dividing by its mass. So you can do it two ways. Either you divide it by per mass, or you can divide even by per number of moles. Okay, so then that are known as molar entropy and molar volumes. Sometimes it is expressed capital S by N, then that is also represented as small s, that is known as molar entropy, and capital V by N, that is also represented as small v, then it is known as molar volume. And especially I draw your attention to the definition of heat capacity and specific heat capacity, where I told you, okay, heat capacity is for a certain amount of mass m, and when it is expressed for unit mass of the substance, that is known as specific heat capacity. The word specific denotes that it is per unit mass or per unit mole. So from the expression or from the unit, you will have to identify whether it is per unit mole or per mole. Sorry, I did not say per unit mole, per mole, or it is for per unit mass. Okay, so we will see how it is related, and dp by dt, you will see that that is usually written as delta s by delta v, where small s and small v are usually used. So this is actually the simplest form of what is known as the Clausius Clapeyron equation. We will be deriving shortly. Okay, now what is its use? What is its use? I told you generally this is a relationship that is used in studying phase transitions. Okay, to be very exact, specific, you can express the Clausius Clapeyron equation in terms of the latent heat. I told you it is useful in first order phase transitions, so there will be latent heat involved. If you are able to relate this equation to the latent heat of the system, then it will help us to predict the changes in characteristic temperatures. What is the characteristic temperatures of the system? Such as boiling point, melting point, sublimation point, etc. So these are the characteristic temperatures. Okay, it depends on the particular system. From system to system, the boiling point is different, the melting point is different. So they are characteristic of the system. They are known as characteristic temperatures. Okay, so for example, that at normal altitudes, like our places and all, water boils at 100 degrees Celsius, right? That is a common. If somebody asks you, what is the boiling point of water? Okay, you usually say that, yeah, okay, what is there to ask? It is 100 degrees Celsius. But if somebody asks you, is the boiling point of water 100 degrees Celsius always? Then you should be careful. No, the answer is no. The answer that you are telling is at a pressure of 1 atm, at normal atmospheric pressure, which we are experiencing at ordinary altitudes. Okay, you know that when you go to higher and higher altitudes, like see, if you are going, for example, if you are going to the top of Mount Everest, okay, you are on a mountaineering mission, and you are going to Mount Everest, where you want to, okay, just have water boiled. Okay, see, will it be easy or difficult, or will you have to heat up to 100 degrees Celsius? Do you think? You will see that, okay, at Everest, you can boil water even at a lower temperature, because there is a change in the pressure. Okay, the pressure at those altitudes is reduced, so there is a lesser pressure. Okay, so you will see that you will be able to boil water at okay, for example, it's a standard result. That is why I'm just mentioning. Okay, see, at Mount Everest, water will be boiling at 82 degrees Celsius instead of 100 degrees Celsius. Means there is a lowering of the boiling point of water by 18 degrees Celsius than the normal. Okay, so means you are why it happened, because there was a change in the pressure. So when there is a dp, that is what I wanted to mention. When there is a change in the pressure of the system, there should be a corresponding change in the temperature. Okay, what temperature we are talking about? We are talking about the characteristic temperature, like boiling point. Means there will be a variation of boiling point with a variation in pressure. There can be variation in the melting point of the substance with what variation in the pressure. Similarly, there will be variation of sublimation point of the system with a variation in pressure. How much the variation happens can be found out by using what is known as what? The Clausius Clapeyron equation. And such phenomena are very common when you study about the phase transitions and its thermodynamics. Hence, that is the relevance of Clausius Clapeyron equation. Okay, so I wanted to give you some introduction about the Clausius Clapeyron equation. Certainly, one thing before we close this session, this will give you just an outline of what we are actually going to learn, right? And next session we will derive the Clausius Clapeyron equation by two techniques. Okay, one by the direct method and other by using the phase diagram technique. Okay, thank you.